Hello and welcome to Mechanical Y. Today we are doing part 3 of a 3-part series of micro lessons on the mathematical equations used to describe conic sections. Now conic sections are created when you take a pair of cones that are joined at the vertex. Now these cones are identical to each other and they extend till infinity in both directions. Now conic section is created when you take a cutting plane and you slice through these cones in a particular way. Now the shape created by the cross-section of this cutting plane cutting through this set of cones defines that conic shape. Now today we are looking at a particular type of conic shape known as a hyperbola. A hyperbola is created when you slice through both of these cones. And the shape that you get looks something like this. So let's look at the mathematical equations that are used to describe hyperbolas accurately. So here I have a typical hyperbola outlined by the red line. And I've put this on a coordinate system, x and y, such that the origin is exactly halfway between the two curves and splits the hyperbola symmetrically around the x-axis and the y-axis. Now we're going to define a bunch of terms that define the exact shape of this hyperbola. But first we must define two new lines. These lines are known as asymptotes. Now in mathematics, an asymptote is a line that a curve approaches but never crosses or touches. So in other words, this hyperbola, as it goes off into infinity, will get infinitely close to this line but will never cross it. And we're going to use these asymptotes to help define a number of other parameters. First, let's start with this line right here. Let's call it A. Now we call A the semi-major axis, with the major axis being the closest distance between these two curves of the hyperbola. Next, we can define what is known as line B. Now B is the semi-minor axis. And it is drawn such that it is both tangent to the curve of the hyperbola and parallel to y. Now we have two terms, A and B. And these terms are very convenient because they are usually given or known, or you can easily determine them. Now let's say we have a point on the hyperbola, x, y. We can come up with an equation that expresses the location of x and y using these two terms a and b. Now that equation ends up looking like this. The distance in the x direction of this point squared over the semi-major axis squared minus the direction of that point in the y direction squared over the semi-minor axis squared is always equal to 1. This is the fundamental equation that represents every point on this hyperbola. Now we can determine another parameter. This parameter is going to be this line right here, closing that triangle with A and B. Now that parameter, C, is known as the linear eccentricity. Now before we define exactly what the linear eccentricity is with an equation, let's take it and let's rotate it downward this way. So it goes along the x-axis. So it'll go in this direction like that. And it reaches an important point here. This point is known as a focus. And a hyperbola actually has two foci. One focus there that we will call F1 and a focus here called F2. So it has the foci F1 and F2. Now, the foci are important points, and they have many, many real-world uses. For instance, if I was a spaceship doing a flyby of a planet, my path is specifically defined by the path of a hyperbola. And the location of that planet that I'm doing a flyby of is at one of the focuses. So focus is a critical point, and you'll see that it'll be used again very shortly. So now we need to define two additional lines. Here we have one line, and here we have another. Each of these lines is called a directrix. Now, it may seem arbitrary, but a directrix is very important. If I take a line and I start at a focus, and I travel towards the edge of the hyperbola, and I intersect it, and I call the length of this line D1. And then, from that intersection, I draw a line perpendicular to a directrix, and call that D2, I get a relationship that D1 divided by D2 is always equal to a constant. And that doesn't matter where I draw these lines or to what part of the hyperbola I draw, so long as one line starts at a focus and intersects the hyperbola, and then the second line starts at that intersection and goes perpendicularly to the nearest directrix. And we call this constant E, and E is the eccentricity. So these directrices are actually very important lines, but we need to be able to define their location a little more precisely. We can define the distance from a focus to a directrix as the value P, and P is known as the focal parameter. Now we're almost done. We need one more parameter in order to be able to get equations for all of these, and you'll see how we use this parameter in a moment. We're going to define one more line. This line starts at a focus, is parallel to y or perpendicular to x, depending on how you look at it, and travels until it hits the hyperbola. And this is known as L. L is the SemiLatus Rectum. And we're about to use it to help get equations for some of these other parameters. First, while defining these equations, let's start with two equations that are common to all conics. This is the equation for the eccentricity as a ratio of the linear eccentricity to the semi-major axis, and that the eccentricity is also equal to the length of the SemiLatus rectum over the focal parameter. Now these are true for all conics, and we're about to use them to get some new equations. Starting with C, we can easily solve for C because it's found as the hypotenuse of a right triangle. So applying the Pythagorean theorem, we can say that C is equal to the square root of a squared plus b squared. Simple. If we take this value for C and plug it into this common equation for a conic for the eccentricity, and we simplify it into a useful expression, we get that the eccentricity is equal to the square root of 1 minus, plus b squared over a squared. So 1 plus b squared over a squared. Now, we know the location of this point up here. We know that this point is the distance c in the x direction and the distance L in the y direction. So now what we can do is that we could take that equation and plug it into this equation, the common equation for all hyperbolas. And then we could do some algebra and combine it with these other terms that we know, and we come up with an equation for the SemiLatus rectum. Now, without doing all the math here, that equation ends up being L is equal to b squared over a. Now we could very easily take this and plug it into this equation for eccentricity and find out that the focal parameter p is equal to b squared over the square root of a squared plus b squared. And here we have the fundamental equations for a hyperbola. We have the two equations that are common for all conics, and then we have 5 equations that precisely define the shape of this hyperbola. Well, I hope you found this interesting. If you did, please like and share this video, and please subscribe to stay up to date on future micro lessons.